I'm very pleased to introduce today's speaker in the fourth lecture in the AMR Recent Mathematical Advances Distinguished Lecture Series. Professor Alexander A. Razborov studied at Moscow State University and the Steklov Math Institute of the Russian Academy of Science. He joined the faculty at the Steklov Math Institute in 1989. From 1999 to 2000, he was a visiting researcher at Princeton. From 2000 to 2008, he held a visiting position at the Institute for Advanced Study. Since 2008, Professor Razborov has been the Andrew McLeese Distinguished Service Professor at the University of Chicago. Professor Razborov has worked in areas including mathematical logic, computational complexity, proof complexity, and combinatorics. His contributions include the first description of solutions of equations in a free group, solving the analog of the P versus NP question for various restricted models of computation, the theory of natural proofs and the closely related area of finding feasible provability for major open problems in complexity theory, lower bounds in quantum communication complexity, and the theory of flag algebras in extremal combinatorics. Professor Razborov is a member of Academia Europea since 1993 and the corresponding member of the Russian Academy of Sciences since 2000. He is a recipient of the Nevelina Prize, awarded by the International Math Union, the Gödel Prize, awarded by EATCS and ACM, and of the David Robbins Prize, awarded by the American Math Society. Please join me in welcoming Professor Razborov as he gives today's AMR-RMA Distinguished Research Lecture.
All right. Thank you very much for the introduction, Joel. And it is my greatest pleasure to talk here. So let me try to get the points. Can you see my screen?
Yes.
Good. So let me now start. All right. So I was told by the organizers to be entertaining, and I will try my best. So it is a general lecture, and some of the topics, actually almost all of them, are very technical when you really start doing things, not only talking about them. Papers are typically 100 or more pages long. So we will not be able to go into any details. I already gave some sources are listed on the talk webpage, and maybe I will think of something more. So it is just an introductory lecture. Let me start with very general philosophical speculation. So no matter what happens. Right. No matter it's on my laptop. No matter what you are doing in mathematics, even if you are interested in classical structures, completely continuous or algebraic structures, then sooner or later you encounter combinatorial objects. That's the rule of thumb. Or whenever you do something on your computer, you have to discretize your program, or if it is Dinkin diagrams, whatever. You can find examples in your own area, and that's the flow of thoughts we are used to in mathematics, which means that discrete objects like graphs or more complicated objects, they appear naturally, even if you don't care about them. So in my talk today, I will try again to give at least some general, very general overview of an emerging area. It's something like 20 years old that tries to go in the opposite direction. So assume that you want to study discrete objects doing combinatorics or discrete mathematics, whatever you call it, theoretical computer science, but you want to apply methods from, well, core mathematics or whatever you want to call it. You want to study your combinatorial objects from this perspective. And of course, there are many ways of doing it. The first area that comes in mind is algebraic combinatorics, very beautiful and large area, but we want to distinguish ourselves today from things like algebraic combinatorics. And this is something that is more or less necessary for objects we are going to study today. So they must be huge, and we really don't care about small perturbations if you say remove or add a few edges to your graph. All right. So I think a beautiful source in this area is this book by Lazarov, and in particular, in chapter 1 is a very skillful and very useful introduction into why should we care about very large combinatorial objects, graphs and others. And so this is one right. There are many examples. As we all know, they appear in the world, or they very large objects appear in the world, in the modern world. They are basically everywhere, and but our focus, as we shall see today, is somewhat different from what people do about it. So, by the way, if there are any questions, then I think it's okay to ask them during the talk. But I don't monitor the chat. Someone else has to communicate the questions to me. All right, good. What? Right, good. So let's start with the most basic thing. If you are going to replace something which is very huge, but by something continuous, then we of course should first understand how are we going to take limits. So we have increasing sequence of graphs, for example. I will use mostly graphs in the first part of my talk because it is, very important case, and because it is easier to explain ideas. But in the second part of the talk will basically consist of deviations from graphs. For now, it is graphs. And it is important to understand here that we don't have any relations between these graphs. It's not like when you take direct limits or inverse limits, they're just coming for every n you have a graph. You don't know anything about them a priori. And then we have the same questions that mathematicians usually ask. First of all, what kind of convergence do we want to study? What does it mean to converge? What it converges to? And if this thing is unique. And let me immediately get to the point. But before I go to the point, let me make this disclaimer that the area, at least as I see it, it is certainly larger than everything I may realistically touch today. So, and let me just spend a couple of slides saying the case we are going to today, and it is the case of dense combinatorial objects. For example, if you have an ordinary graph, then, it is, technically speaking, it's n shows 2, but we don't care about small perturbations. So its H density is about this value. And for the whole area, it is important that densities is what we are interested in. We are not interested in n at all. We are interested, for example, in what is the fraction of edges in my graph. And the case we are going to study today, we are going to talk about today, is only dense regime, which is well-developed theory, as we shall see. And yeah, that's what we are going to study today. And so just to give some idea of what is skipped, there is very interesting sub-area which is called sparse regime. When you really want to talk about bounding degree graphs, which means that the H density is roughly 1/n up to a constant. And Lovos has the whole chapter in his book about this case. It's very interesting, but again, for the lack of time, we will not do it. And also, what is even more complicated is intermediate regime, where it turned out to be not so easy to even define limit objects. Or what does it mean? Well, they were called graphexes. You need some Poisson processes. And again, I will not touch it. We will talk today only about the dense regime. Okay. So the fundamental notion here in this theory is sampling. As I said in the first part of my talk, I will deal only with the case of ordinary graphs. So, and it is defined very naturally. Namely, I have G, and the idea is that G is large, its size grows to infinity, and I have a fixed graph H. Then it is simply on k vertices, then it is simply our main quantity. It's simply defined as the probability that if I pick k vertices in my graph, then I will see something isomorphic to H. And for those of you who know a bit of this theory, when you talk about ordinary graphs, it often makes sense and it is more natural to talk about so-called graph homomorphisms. Basically, these are mapping from vertices of H to vertices of G. They need not necessarily be injective, and they only have to preserve H's, but they may create new H's. So depending on the context, these two versions, some of them are good in one context, some of them are good in another, but what I can say mathematically is that actually, at least for this theory, there is not much difference between them because you can always go back and forth from this to that using some simple Möbius transform. So from the theoretical point of view, you can use whatever you like. And now comes our first and basic definition. And if you ask for justification, then the best justification I can give is that we shall see it during the talk, that it is the right definition. So the right definition is simply says that this sequence is convergent if and only for every fixed template H, for every fixed graph H, those densities converge to a number, which I will denote phi of H. All right. So, and here are a couple of remarks, and I think they are self-explaining. So the second, for example, says that there are lots of convergent sequence.
I'm sorry. I've got a question about, so in the previous slide, you defined the version with up to automorphisms. So I understand that there are either you're considering labeled graphs or unlabeled graphs. Is that the case? And so which one are you considering here? Unlabeled graphs or labeled graphs?
Excellent. There are 3 or 4 different versions of defining it. One of them is with labeled graphs, another is with unlabeled, and all of them are equivalent up to a linear transformation.
And which one are you considering? You don't care.
Unlabeled.
Just
Unlabeled.
unlabeled. Okay.
And since the question is here later on in 10 or 15 minutes, I will say exactly why it might be important in certain contexts. Thank you very much. More questions? All right, good. But again, since all versions they are equivalent up to a linear transformation, then it does not affect convergence. Okay, that's what probabilities are. And now comes my extremely speculative slide. So far, from every convergence sequence, we have this bunch of numbers between 0 and 1 because these are densities. And so let me just, maybe I will go quickly over it. So and now we can study it. We can study these tuples of numbers in two different ways, like algebraically, simply what properties they satisfy, or geometrically, well, what objects they describe. And so there are many obvious analogies here in mathematics, in logic. And in this area, again, for ordinary graphs, it is what is called log algebras and graph limits, algebraic and geometric view. And I will talk a bit about both. And this word cryptomorphism, I like it very much. I looked it up. It was introduced apparently by Birgov many 70 years ago or so, used by Rota. Loesch used it in its book. So cryptomorphism is something which is like isomorphism or homeomorphism, but not exactly. So when you morally understand that two classes of objects are sort of equivalent, but you really don't care to make it rigorous, to make a category or something, and then you say cryptomorphism. I love this word and I am going to use it. Good. So let's start with algebraic characterization. It is log algebras, and I will be very brief here because for obvious reasons, I love this topic. Well, I spoke many times about it, but to do it properly, you need the whole lecture. So I will do it very quickly. So it basically repeats what we already had. So we have a convergent sequence, and then we have this mapping. And the idea is, I will show just a couple of details on the next slide. But the idea is that those sequences, they can be identified with homomorphisms from a naturally defined algebra into the reals with certain positivity conditions, non-negativity conditions, I should say. So I will briefly say later what 0 stands for, and plus stands for positivity. So let me just give you some cartoon example how it works. So if I have all those densities denoted by phi, then I have linear relations between them, because if I want to sample two vertices from my graph, then I can split it into steps. First, I sample 3 vertices, and after that, in that 3 sample, I subsample something which has only 2 vertices in it. Then by the law of total probability, or whatever you call it, this density can be always expressed as linear combination of those densities. And we make the usual stuff about it. We look at all formal linear combinations of all those things, and we factor it out by linear relations. So phi respects all these linear relations, we factor out. And a slightly more complicated thing that you can do is also to look at multiplication. For example, again, cartoon example, if I want to square H density I will denote by rho. If I want to square H density, then I can do it like it is shown here. Namely, I can first sample 4 vertices and then look at what I see. Here it is not exact operation, because if I sample these 2 vertices and those 2 vertices independently, then I may get a collision. right? Some of the vertices may coincide, so it is not. We always have an error for finite objects, but we are taking the limits, and when the size of your graph grows, then the probability of collision also becomes negligible. So it gives you multiplication, and then you routinely check that it all works out, that you have really algebra, and it is my A0. So, and then the first cryptomorphism, it simply says that converging sequences is the same, essentially the same as these purely algebraic objects. In one direction, I sort of explained it. So if I have a convergent sequence, then it will give me an object from a homomorphism, positive homomorphism from this class. And in the opposite direction, it does require a proof, but it's not, this one is not difficult. You can do it. And at this point, I'm sorry, I don't know what. So, and at this point, you probably want to ask, is it only about definitions and some equivalences and other abstract nonsense? And here is my hopefully honest answer. Let me show you, at least mention some applications, because all this abstract stuff eventually leads to very concrete results in extremal combinatorics. And I will do it very briefly again, because I did this talk. I gave this talk only about this subject many times. So I will try to convey at least some ideas, but the idea is that many problems in extremal combinatorics, they can be formulated, or at least maybe in slightly more complicated way, as proving that some elements in my Flock algebra are positive, which means that if you evaluate them by an arbitrary homomorphism phi, or arbitrary convergent sequence, we already know it is the same, then you will get something non-negative. So when you really want to apply this stuff, then it is important for purely practical reasons that will appear on the next slide. It is very important that we don't work only with this algebra, that we consider its relative pointed versions. I, again, don't want to spend time on trying to explain them, to define them. It is simply you fixed a certain number of vertices in your graph, and you require that all mappings in you call it a Flock, and you require that all mappings you consider to compute densities, they should preserve those versions. Then you have, again, I'm going to skip it. Then you can have.
I'm sorry.
Yeah.
Sorry, I didn't get. So, what is the definition of positive? So, positive does not mean you just take positive values. It means that the sum of values on sum of squares.
No. You mean this positive, yeah?
So there was a positive before.
This one.
So that's the only positive you've been considering.
Yes.
Okay, and so the definition is.
So if phi is a homomorphism such that phi of any h is at least 0, then phi of this expression is also at least 0. Yes. No.
I'm sorry. So being positive means that phi of any f positive is going to be.
No. It means positive means that phi of any h, where h is an individual graph, its density, right? It's between 0 and 1. Or let me make it back. Here. This is the condition. So it is. It should be true that these values are always non-negative. They are between 0 and 1. They are densities. Okay. Right, so this is an evaluation operator. Let me not say what it is exactly, but anyway, it turns out that after you formulate things in this way, then you get positive semi-definite programs that you can really solve. Well, even given simple tools, you can really solve them for objects on many vertices, and sometimes or often it leads to new results in external combinatorics. You can prove these things, and this is where it is extremely important that you consider the version P, because and that you take into account fully take into account all existing symmetries. So it gives you smaller programs that you can actually solve. So, and let me show, before we move on, let me just show a couple of results. There are very interesting general results, somehow surprising if you know a bit of mathematical logic. For example, this is, I think, extremely surprising result, that this relation that looks very innocent turns out that it is algorithmically undecidable. It was proven almost 15 years ago. And it is a very important conjecture in the area. So let me spell it. It is a bit inconsistent notation because this conjecture and that result, they are formulated for homomorphisms, but the idea is that the density of H is at least what you get in a random graph with this H density. So, and this is also a refinement of this thing, because in Hatami-Norin result, like in all results of this sort based on Matei-Savich theorem, it's all very unnatural. So it is the simplest non-trivial case of Sidereko's conjecture, known case, that if I have a path on four vertices, then its density is at least cube of the H density. Then turns out that this thing also does not have a proof of the kind I showed on the previous slide. And again, I can talk about log algebras for a very long time, but let me stop it here. Let me just, that's the source I was, the recent source I was able to find. You can, it is Bernard Lidicky's slides for workshop on log algebras. So 5 years ago, you can see from this source what was known 5 years ago. Now we have twice as many results at least. And if there are any experts in the audience, then I would really appreciate if you know any more advanced, more recent source on applications of log algebra. But I really prefer to stop it here, because otherwise I will not have time for other things. Questions?
So what is a flag algebra, and why do you call it a flag algebra? Is it A? A is the flag algebra? Okay.
Yep,
And
yep.
why flag? Because you've got vertex included in, I mean, it's for graphs, I guess it's for one flags.
Yeah, no, the choice of name was more or less arbitrary, but the idea was that if I have a fixed number of a certain number of fixed points, all right, which don't change, then, and the rest of the graph or of your model it changes arbitrarily, then it just reminded a waving flag. All right, so it's as good word as any other. I really don't know. So it's a good name. All right, good. So let me now move to geometry. And again, for ordinary graphs, it was developed in this paper by Balash, Segedi, and Latzelovash. So we start with the definition of a graphon. So you can put here arbitrary measure space. It does not matter. instead, no, sorry, here instead omega, but let's take 0, 1. And what is the intuition? The intuition is that, think about it, you obviously cannot do such things. Measure theory forbids you to do it, but you still can think about it this way, that I connect two vertices x and y with probability w of xy. It simply does not exist. You cannot do such things. But let's not care about it. Then what you can do, you can define in the natural way densities of any h in your graphon w, and then you will have right here. Here is, for example, triangle. Click on three vertices. So it is defined naturally. You take this product, of course, and you can do it for arbitrary graphs. And let me denote phi w, something which comes from graph. Sorry, something which comes from the graphon w, this mapping, and then there is this another cryptomorphism. Namely, turns out that it corresponds to convergence sequences. It's relatively easy to prove in one direction. If I have a graphon, then how to come up with convergence sequence, and it's very difficult in the other direction. So the original proof used Simulated regularity lemma, if you know what it means. So it can be replaced with ultra filters. It can be replaced with exchangeable arrays, but you really need heavy machinery to go in the opposite direction. And the reason why it is so difficult is also sort of clear, because as I said, we don't know anything about my sequence of graphs, except that all densities converge. And you somehow have to combine them in one structure, in one graphon, and so it is not so easy to do. But anyway, the end result is that this will also describe the same object, which of course mathematically very good. That's three different definitions result to the same thing, and there are maybe 6 or 7 different definitions. Let me just briefly mention yet another one, which has somewhat different flavor. So we look at now these are labeled graphs. We look at all labeled graphs on countable set on integer numbers, and we look at probability measures on those graphs. So it is symmetric if it is invariant under this group of permutations, and it is ergodic if it is a vertex in the corresponding convex body. If you look at all symmetric measures, then it is a convex body, and you look at vertices in this convex body. Well, it's infinite dimensional, but you don't care about it. You look at a vertex. So it turns out that these things are also cryptomorphic to anything we did before. So it's yet another characterization. There are maybe 2 or 3 more characterization of a similar flavor. Anyway, it's a good object to study. And uniqueness is also takes place. And again, it is not easy to prove. Nothing in this area is easy to prove, even if it looks obvious. But the uniqueness was proven in the natural way. Only you need here some intermediate graphon W. So basically, so graphons are equivalent in the sense that they correspond to the same element from, I don't know, homomorphisms from the Flag algebra, if and only if. You can write them this way, or you can also rewrite it in terms of so-called cut distance, but I will not talk too much about it. So any questions? Because it basically concludes the first part of my talk, which is devoted to more to all the results and mostly by other people. Questions? Right, very well. So now we move to the second part of our talk, which represent more recent work. So, and the first thing we want to do is to move beyond graphs. So we will see how well I proceed. So this framework was actually already introduced in my paper of log algebras. Turns out that the language of mathematical logic is very useful here. But if you prefer to do it without using this language of model theory, then basically what you need a class of structures with these general properties. If you have a structure, then every set of vertices induces a substructure, which, for example, rules out things like groups and rings, because it is violated there. But there are many structures that have this property. So I just listed some examples. So you can take all flavor of graphs, oriented, non-oriented, hypergraphs, tournaments, directed. So you can, for example, do colorings, you can do equivalence relations, you can forbid some structures, which is also closed under taking subgraphs. And right, and also it also happens all the time in combinatorics. You can combine several structures on the same ground set. Like you can color vertices, you can color edges, you can introduce equivalence relations, you can introduce a linear order, and you can do all these things. And it covers quite a lot of normal combinatorial structures. And sometimes you can even put here structures that are intuitively not obvious. For example, if I look at permutations, then if you realize permutations in this way, then clearly it does not conform to my definition, because if I take any subsets, then unless you are lucky, there is no permutation induced on this subset, but you can slightly change your view. You can view a permutation as just a couple of linear orderings on the same ground set. Sometimes that's how it is defined in algebra, and viewed this way, it is certainly part of the theory. So what else can you do? Another example, you can do words. So how to do it? So you look at the word in the finite alphabet as simply the theory of linear order, so which defines your ordering of your letters in your words, and you have, say, in this case, 5 color, or well, in this case it's not 5, I think it's more than 5 colorings in different colors corresponding to letters, and again, it will give you the theory, and there are many more examples like that. Many normal combinatorial structures, they fit into this framework. So again, my original paper on log algebras in all 7, it worked within this level of generality. So in particular, all that stuff, you can define it for arbitrary theories with my restrictions, or arbitrary combinatorial structures, and you will have all the same things. But geometry turned out way more difficult. So, and to explain why it is difficult, I would like, I should start with the case of hypergraph forms. Hypergraph is a generalization of a graph. For example, 3 graph is just a set of unordered triples of vertices in your graph. And the naive attempt how to generalize graph forms to hypergraph forms, it does not work out. So, and here is the classical example. So if I look just at a random graph and take a set of all triangles in this graph, then I will get a 3 graph with density something like 1 over 8 or 1 over 8, because everything is independent. But what I will get as in the limit as a hypergraph form will be different from the experiment where I simply take every triple independent. So we need to do it right. We need high order coordinates and
Actually, you're a bit fast. Could you please repeat slowly the previous slide?
Okay, good. So from the beginning.
Yes, so
Good. So we want now to generalize it to 3 graphs, 3 graph forms. Okay. So this is how a naive generalization would look like. So it's simply a graph form is a symmetric function on pairs. You may want to just define it as symmetric function on triples. It does not work. I mean, all these things, they are legitimate hypergraph forms, but there are others. And here is an example of how to define these hypergraph forms. One good example, if I look at the random graph, Rorty random graph simply means random. And if I take all triangles in this graph, then I will get, well, 3 graph of density 1 over 8. Okay? Because everything is independent. And I can also just include every triple with probability 1 over 8 with the same probability. And these 2 objects will be different.
okay, I see. Thank you.
Mm-hmm. So, and that's how you do it. I think, right. So I will not try, I guess, to fit into my talk more material than fits here. Let me finish one part, maybe another, and then I will stop. I put some references on the website, and this is the general idea how you do it. So you can view an ordinary graph form as simply something which depends on vertex, on the pair of vertices, and here is some not interesting coordinate. What you have to do here, Leonid, I don't expect you to completely understand this part. Right. So if you do, it means that I'm doing something wrong. It's just to give a general idea, because as I said, to define these things and prove something about them, it is difficult. I'm just giving general idea. And general idea is that you have to do the same thing as before, only you have to introduce higher order coordinates. And I skip all the formulas. And after that work on hypergraph forms, there were many generalizations for different combinatorial objects. And what we did is a general theory, which again is mostly a bunch of definitions, but at the end I will show some interesting open problem. And again, right, I don't expect you to understand formulas here, unless you have seen them before. I mean. So, but we try to follow the same pattern as when you do model theory in mathematical logic. Namely, you have a theory, it has a bunch of predicates. For every predicate, you have its interpretation that we call peon. P stands for P as in predical symbol, as in PI. So, and we don't impose any symmetry assumptions here, unlike hypergraphs. It's not necessarily symmetric and no axioms. And after that, we introduce axioms. So, again, like in model theory, you can naturally define if you have a quantifier-free formula, first-order quantifier-free formula, and we are not interested in quantifiers here, and you have a structure, then you can define a measurable subset, give its truth definition. It is all doing nature. It is all done naturally by construction of the formula F. We can simply define the set of all those things where my formula F is true. Again, so it's 1 or 2 slides of definitions. I cannot do it here. I can only give a general idea. And then we can define what is a theon, and there are basically two possibilities here. So each is my truth set if I take any axiom of my theory and look at the set of all points in this crazy set where it is satisfied. What we can say, we can either say that its Lebesgue measure is equal to 1, which means that my formula is true almost everywhere, or we can say that it is true everywhere, well, except for the diagonal. I would prefer to sweep it under the rec. So, basic possibilities is to say that it is true even either almost everywhere, or it is just true everywhere except for this set. And then everything, again, I am skipping lots of details here. Everything, geometry works through them. So for an arbitrary theory, it works through just in the same level of generality as it did for flag algebras. So for arbitrary theory T, we have convergent sequences defined in the same way. We have theons, we have homomorphisms, other descriptions from Lawler's book also work through. And we also have existence and uniqueness, but uniqueness, even conditions are extremely complicated. I cannot hope to meaningfully say here what those are. All right, so it's basically, well, it's more than 100 pages long, but it's basically a service paper that essentially says that things that geometry that works for graphs, it also works here. So let me now show you at least some beef. Yeah, so that's what I just said. Let me now show you at least some beef and an open problem. So it is very popular topic in modern combinatorics, removal lemmas. So they came in different flavors, but here is the main paradigm. So if you have large object and it has a few copies of smaller object, combinatorial object, then you can change your large object in a few positions so that it will contain no copies of them. Right? So, and it is just to remind the definition, our definition of reconstructions, and if we look at the theory that forbids copies of M, then it actually it has very direct analogs here. So what does it mean now if I replace finite objects with theons, with infinite objects? What does it mean that there are only a few copies? It means weak theon. It means that the measure where I have these copies is equal this axiom, which says that it is a copy of M, it is satisfied almost everywhere, and strong sions means that there are no copies of M at all. So, and that's one of our results, which is very somewhat non-trivial, because it simply says that if I have any weaker tion, which means that I allow measure zero errors, then I can always rectify it by changing in a measure of in a set of measure zero, so that all my axioms will be completely satisfied. So
Does this go via semi regularity? Does
what?
this go via semi regularity?
Nati, very good question. Thank you very much. It goes no. It does not. You use hard stuff, semi-regularity, or I don't know, ultra filters to prove the existence of cions and their uniqueness if you need it. But after you do this hard work, then you just use its results. That's what it uses.
Thank you.
That's what it uses, but turns out that it uses axiom of choice. Surprisingly, you basically write down a set of propositional constraints you want to satisfy, and you prove that every finite set of them is consistent. Therefore, they all must be consistent. So, and if you don't care about axiom of choice, then here is a concrete form of asking our open question. So if you have if your original tion n is Borel, if all those sets are Borel, then can you also ensure that this thing will also be Borel? It's morally equivalent to asking for a constructive proof. So we don't know the answer, and we were able to prove it for very simple cases. And for example, for linear orderings, it should be obvious, right? So I give you a measurable linear ordering of omega of 0, 1. Can you always, which is almost linear ordering, almost satisfies all axioms, can you fix it in such a way that that it will be actually linear ordering without any things? But even that is 4 pages of a proof or something like that. And so this is, I believe, the simplest case that we know, and in a different language, it had been asked by Lopes. All right, good. So any questions? Then I have something like 8 minutes, and I have 2 more topics. I think I will just go over one of them. I will be happy to contribute slides, of course, to the web page. So it is the theory of quasi-randomness. Something is wrong here. So it is very important theory in combinatorics that started in that seminal paper, which is almost 50 or whatever, 40 years ago. And there were other papers also on the subject around the same time. So, and the idea is, in terms of converging sequences, the idea is to capture what does it mean that your sequence of graphs, it looks like random. For example, if I sample it from the Erdős-Rényi distribution, so n is the number of vertices, p is the probability of an h, and it means that every h is sampled with the same probability, then there is no ambiguity here. There is only one theory of quasi-randomness for ordinary graphs. Whatever you do, all roads lead to Rome. There's
Sasha, can I interrupt with another question?
absolutely.
Was it a complete coincidence that before you spoke about C4, and C4 plays such an important role in this theory of Pseudo randomness?
I believe it is a coincidence.
Okay, thank you.
So C4 is simply simplest graph. For 3 vertices, you can do it. I guess you can do it for paths or for something like that. I mean, we are now talking only about series of this form that you forbid something. So for triangle-free graphs, I believe we can do it. It may even follow from our Horn results. It's simply the simplest case where we cannot do it. I cannot see any direct connections, but it is an excellent question. Yeah, so as Nati mentioned, there are very many characterizations here. One of them simply says that the density of C4 is what it is going to be, and it will be equivalent to all these things. But anyway, there is only one theory for ordinary graphs. And that's it. So, and obviously people try to generalize it to other combinatorial objects. What does it mean, for example, to have quasi-random three or three graph, hypergraph, or something else, or tournaments? And there were quite a few papers, but now things became to look more interesting in a sense, because you really have a hierarchy of your properties, of random properties, and it's a structurally more interesting picture. So, and right, that's again somehow, or that is related to Nati's question. And you basically here for ordinary graphs, C4 is just one of the many definitions. It's not essential here. You forbid, sometimes you do it ad hoc. You forbid octahedras or things like that. So it is based on concrete densities. And again, what our goal was to come up with a theory of quasi-randomness that would be natural in a sense that, well, mathematicians would call natural. So, and here are our two main properties, what we need from our theory, or our self-imposed restrictions. First of all, we really want it to work in the general situation. We don't want one definition for 3 hypergraphs, one for 4 hypergraphs. It really should be uniform, and also it should behave naturally, and I guess that's why we used this name, because there is a natural category. Again, I am bound to skip many things here. The idea is that if I give you a quasi-random object, then you really cannot construct from it anything that does not look quasi-random in our sense. These are two restrictions that we imposed on ourselves. And let's see, I still have 3 or 4 minutes. Let me show something. All right. Somehow it doesn't work well. And let me just, these are 3 main classes that we were able to identify. All of them become the same. Everything we do is collapses to the standard definition for graphs. So very briefly, key independence, it means that you can somehow, you can take your limit object and represent it in such a way that it will only depend on higher order coordinates. So this is, in a sense, dual property. We say that if I take my object and I try to couple it, I mean, couple in natural sense, put two structures on the same vertex set, then you will get, then there is only one possibility of doing it. You can couple it at random, and the third group of properties, it says that if I try my object and k-induce it, again, I cannot give any details here, look at the paper, but anyway, what I will see, it will be identical to what I started. And all of this is a direct generalization of several definitions of various definitions for ordinary graphs. And the picture, as it shows in our paper, is turns out it's very interesting. So that is copied from our paper. So these properties, they look very different, but they relate to each other in very interesting way. And let me finish with one sort of cool stories. First of all, I had mentioned hierarchies of quasi-random objects for hypergraphs. Well, it is one paper that tries to combine them together, and somehow they go along different dimensions. There are almost no relations with our hierarchies. It's our hierarchy, and so it really took from them several years of work, and the paper is more than 100 pages old, more than 100 pages long, to prove that there is actually this implication. And I perhaps will just indicate why it is very difficult, because so if you look at the definition of couplability, don't know how to pronounce it, then it is universal, right? It says that if I have any pairing of my object with something, then I will get something. It's universal, and this one is existential. It simply says that if I have an object, that I can sort of tweak it in such a way that it will become simple. And as we all know, proving that universal statement implies existential is not often not easy, and in this case it turns out way more difficult. And anyway, now this is how the relation between these classes looks, and now it is complete, which means that we have separations between all pairs of classes that are not explicitly shown to be related to each other on this picture. All right, good. So I think my time is almost over, so it is my last topic, and let me just say that it is a cool paper that I highly recommend to look or looking through. It is very provocative and intriguing applications of this stuff to machine learning. In machine learning, so I skip everything. In machine learning, one of the main assumptions in theoretical machine learning is that when you sample your data, you do it uniformly, right? Otherwise you are dead, and there were several attempts to relax it, but not very successful. It's uniform sample. It's important for everything you are doing. And but if you sample, for example, from a graph, then it makes little sense to sample ages, because what you will see a matching. You don't gain any information about your original graph. You know it's
Sorry, Sasha, who are C and M? The initials of CM. Who are the authors?
Here.
Okay, thank you. Okay, thanks.
No, I am going. I'm going quick because I am out of time, more or less. So when you sample from a graph, be it machine learning or not, then it does not make sense to sample ages at random. You will not see anything. You will see a matching. So it is more natural, way more natural, to first sample fixed number of vertices, and then ask your learning algorithm to be revealed all connections between those vertices. And you can do it, and the paper traditionally the paper is over 100, maybe even 150 pages long, because in this area it is very easy to come up with a great idea. When you start realizing it, it becomes different. All right, so I think I'm slightly over 1 hour. I think it's a good time to stop. Thank you.
Let's thank Professor Razborov for that excellent talk, and then I think we have some time for questions. So just unmute yourself and ask a question if you have one.
I have
Thank you.
the following question.
Let's start with
Is the convergence of graphs which you described at the very beginning metric in some sense? So can
You can do it. You can do a metric, but one problem, yes, you can do it, and it's sometimes convenient, but the problem is that this metric is not natural in any way. There is no natural way to introduce this metric. Unlike topology, there is no natural way of doing it. You simply have to enumerate all graphs and sum those things with coefficients like 2 to the minus k. It will not be natural.
When you said that your theory is resilient to perturbations, how you measure what is a small perturbation?
Little o of the size. Little o of n to the k, where k is the average of the predicate you are using.
I see. Thank you.
In the density sense. Everything here is in the sense of densities. The density is little of 1. You call it small. It's just the same as in the triangle removal lemma.
Thank you.
I'm sorry.
Go ahead.
At some point you mentioned you had something, you said something like there is no proof in sum of squares spirit. And I was wondering, so afterwards you seem to have a rigorous way of saying this does belong to the theory, this does not belong to the theory, and this has a cryptomorphism. I mean, this satisfies the cryptomorphism, and this does not. So I was wondering if your methods would enable to recover the non-constructability of certain numbers. For instance, the impossibility to trisect or by saying by Galois theory, saying, well, I cannot solve an equation with radicals using this first order theory because radicals behave like this or that. For instance, using continued fractions, or if ever the group, it does not satisfy one of these small patterns, which is solvable group, and if it does not belong to the theory of solvable groups or something like that. If your methods could apply like this.
So by methods, you probably mean Flog algebras, right? That's my
yeah. Yes, and in the context that you mentioned afterwards, where you were where you were defining these theories, but in an appropriate theory, in appropriate language.
If you can, so the answer here, the honest answer here is that it is not a universal tool. In many cases, it produces results. In many cases, like here, it does not. So it really depends on the context. So, and even if and as far as I understood you, even if your problem does not fit into the framework as it is, because solvable groups are not here, right, period. They use functions, and then sometimes you can you can try to massage them so that they will fit in the theory, into the theory. And the best example I know, which is also in the survey, well, it's basically a survey, is phylogenic trees. The Noga Allen and a few other guys. So they looked at a framework which obviously, well, a priori is not a part of, does not satisfy our restrictions, but somehow you can massage them. So my best answer to your question is that it depends on the context. One has to look at the problem, but I hope I did not create an impression here that this tool is universal. You try to apply it to your concrete problem. In most cases, you fail. Sometimes you succeed, but the number of cases in which it was successful is already increasing. It depends on the context. That's the best. We should look into details. That's the best answer I can give.
Okay, so there is no, I mean, there's not much done for the group on in group theory, for instance, or limits of polynomials defined, I don't know, for instance, on a finite field or over Z. But let's say like limits of things like that, and or algebraic numbers or equations. That does not that is
not as far as I can see. In this context, I really don't see how to do it, but also I would like to draw attention to this particular result or series of results because it connects very classical sum of squares, just polynomials, to this stuff, and there is also a story about it. Or just before they did it, I had told one of our esteemed colleagues, whom I prefer not to name, that it is absolutely impossible. It was an AMR-RMA, and then they did it, so they were able to connect it to classical polynomials. So for the class of problems you are describing, I would better advise to look at the classical theory. Sum of squares is a huge area now in theoretical computer science, and I believe that classical sum of squares is more likely to give the kind of connections you're asking for.
Any other questions? Okay, hearing no more questions, let's thank Professor Razborov again for that beautiful presentation, and
Thank you.
And I hope to see you all at the next AMR-RMA lecture.